What is clustering? Clustering is the categorization of objects into different groups, or more precisely, the partitioning of a dataset into subsets or clusters or categories so that the data in each subset ideally shares some common trait, often according to some defined distance measure. So basically clustering is the classification of objects into different groups where each group or dataset or subset, or in other words cluster or categories, has particular traits or properties common to other elements of that group or cluster, and this is done often according to some defined distance measure, which we will discuss in coming slides. Hierarchical clustering. It is also known as agglomerative or bottom-up clustering. The steps are: compute all pair-wise pattern similarity coefficients, place each of n patterns into a class of its own, merge the two most similar clusters into one, replace the two clusters into the new cluster, recompute inter-cluster similarity scores with respect to the new cluster. Repeat the above steps until there are k clusters left. K can also be 1 in this case. So we are given a target value of k, where we have to determine k clusters in the data set. And first we compute all pair-wise pattern similarity coefficients. So given a set of data set of n points, for each of two set of pairs, where pair can be of two data points, we compute the pairwise pattern similarity coefficients. So based on some coefficients which are similarity coefficients, we determine the pattern wise similarity and place each of n patterns into a class of its own. So we take a set of n patterns into a class, new class. Then we merge the two most similar clusters into one. So where there are two similar clusters, we merge them into one. Replace the two clusters into the new cluster. So basically this is the merging only. And recompute inter-cluster similarity scores with respect to the new cluster. So in the new cluster we compute the inter-cluster similarity scores and repeat the above steps until there are k clusters left. So within a new cluster we compute the inter-cluster similarity scores, and we again determine new clusters in the new cluster, thus dividing that cluster. So repeat these steps until there are k clusters left. So the other approach to hierarchical clustering can be divisive or top-down approach, where steps are: start at the top with all patterns in one cluster. The cluster is split using a flat clustering algorithm. This procedure is applied recursively until each pattern is in its own singleton cluster. Based on some clustering algorithm, we keep on splitting the clusters until each pattern is in its own singleton cluster. This is divisive or top-down approach. Next, we discuss k-means clustering. The steps are: choose k initial centroids or center points. Then each cluster is associated with a centroid. Then each data object is assigned to the closest centroid. The fourth point is the centroid of each cluster is then updated based on the data object's assignment to the cluster, and repeat the assignment and update steps until convergence. So I'll discuss k-means clustering the example in coming slide. K-means example is discussed in this example. For k here is 3. So we are dividing the data set into 3 clusters. So k is given as 3 in this k-means clustering algorithm. So step 1 is make random assignments and compute centroids. So centroids are these big dots here, this red, this blue, and this pink. Assign points to nearest centroids to make k clusters. So we assign points to the nearest centroid to make k clusters here. So these blue dots are nearest to this blue centroid, so they are one cluster. These red dots are nearest to this red centroids, so they are the red cluster, and similarly for the pink cluster are made. So three clusters are made with these three centroids. Recompute centroids for each of the clusters, thus updating the original centroids and repeat above process till convergence is achieved. In this example, solution is now stable. So previous example had this pink centroid somewhere here. So, but we computed the centroid for these 4 or 5 points, and this comes out to be this point here. So this is our new centroid, and this is the new centroid for the blue dots. This is the new centroid for the red dots. So we again repeat the above process till convergence is achieved. That is, no more dot is classified into another new class. All dots remain in their own classes. So that is stable classification. Now we discuss fuzzy C-means clustering. It is an extension of K-means. It is hierarchical. K-means generates partitions. Each data point can only be assigned in one cluster. So fuzzy C-means allows data points to be assigned into more than one cluster. So this is saying that in K-means each data point can be assigned in only one cluster, but fuzzy C-means allows data points to be assigned into more than one cluster. Each data point has a degree of membership or probability of belonging to each cluster. It is frequently used in pattern recognition. So K-means algorithm is discussed now. For a given cluster assignment C of the data points, compute the cluster means Mk, which is given as Mk is equal to I, such that Ci is equal to K summation xi divided by n of k, where k is equal to 1 to capital K. For a current set of cluster means, assign each observation as Ci is equal to argument of minimum of xi minus mk whole square. I is equal to 1 to n and k varies from 1 to capital K. Applications of k-means clustering. It is relatively efficient and fast. It computes result at OTKN complexity. That is a big O notation for TKN, where n is the number of object points, k is the number of clusters, and t is the number of iterations. So it's basically a, cubic polynomial complexity. So k-means clustering can be applied to machine learning or data mining very easily. Use an acoustic data in speech understanding to convert waveforms into one of k categories, known as vector quantization or image segmentation. So k-means can be used on acoustic data in speech understanding to convert waveforms into one of k categories, known as vector quantization or image segmentation. It is also used for choosing color palettes on old-fashioned graphical display devices and image quantization. To conclude, K-means algorithm is useful for undirected knowledge discovery and is relatively simple. K-means has found widespread usage in lots of fields, ranging from unsupervised learning of neural network, pattern recognitions, classification analysis, artificial intelligence, image processing, machine vision, and many others. Some applications of clustering are discussed now. First is data mining, second is pattern recognition, next image analysis, bioinformatics, voice mining, image processing, text mining, web cluster engines, and weather report analysis. So all these use clustering for their algorithm, and for these one of these k-means or other algorithms that we discuss are used. Difference between k-means and hierarchical clustering. Hierarchical clustering can't handle big data well, but k-means clustering can. This is because the time complexity of k-means is linear, while that of hierarchical clustering is quadratic. That is O n square. In k-means clustering, since we start with random choice of clusters, the results produced by running the algorithm multiple times might differ, while results are reproducible in hierarchical clustering. So In k-means clustering, since we choose the centroids at random, the results produced by algorithm running multiple times can differ, but it is same in hierarchical clustering. K-means is found to work well when the shape of the cluster is hyperspherical, like circle in 2D or sphere in 3D. So it is K-means is found to work well when the shape of the cluster is right spherical in a dimension. K-means clustering requires prior knowledge of K, that is the number of clusters you want to divide your data into. But you can stop at whatever number of clusters you find appropriate in hierarchical clustering by interpreting the dendrogram.